Hello, in this video I'm going to talk about planetary nebulae, which are popular objects with astronomers because they can result in photographs like this one. This is the Ring Nebula M27 and one of the bright planetary nebulae in the Northern Hemisphere. But first of all, before we get into what they are and how they form, let's clear up the name because the name is misleading if you don't know better. Because planetary nebulae have got nothing to do with planets, and they're also not nebulae in the way that we tend to use the word nowadays, as in a star formation region, because they are actually the end point of a star's life, or nearly at the end point of the star's life rather than the beginning. So if we go back to when people were first observing these planetary nebulae, along with nebulae and galaxies and supernova remnants and such like, they all looked like these diffuse, fuzzy, cloudy blobs through these early telescopes that they were using. And planetary nebulae looked like dim planets. So you could resolve a disk or a near disk because they have a sort of near circular shape. So you could resolve this disk, but it just looked dim and a bit fuzzy. The disk looked a bit like a planet. The fuzziness looks, well, that gets the name nebula. You know, all of these objects, galaxies and some of the supernova remnants and such like, they were all cloudy. They were all nebulous in the way that they looked. So this is how planetary nebulae got their name, because they looked like cloudy, faint planets. But of course, they got nothing to do with that, as if you watch the video that I've done on the life cycle of stars, or you know anything about that anyway, then this is the end point of stars that begin their life from sort of 0.5 to 10 solar masses. So these are the medium mass stars. These are the main sequence stars when they start off their lives. And as they get towards the end of their life, so they expand out to be red giants when they move into a later phase of fusion, when they've got a shell of hydrogen fusion going on around the core. The star has expanded out to be a red giant. So they've got lower density. There's a lot of turbulence. There's a relatively large wind going on, a solar wind going at a stellar wind away from the star. And the outer layers of the star get pushed away. So they're getting blown away in a wind type setup. So not blown away in an explosive supernova event that we see in the more massive stars, but more getting pushed away. So it stays, it's got some sort of structural integrity. It's moving away as a sphere relatively slowly, at least compared to a supernova. And all of this material is getting pushed outwards, leaving behind a white dwarf, the core of the red giant star. And that white dwarf, which is really, really hot, 30,000 Kelvin, something like that. And that then heats up and ionizes the material that's been emitted, which is now this gas, which is in a sphere around the central white dwarf. And it ionizes this gas, which then causes it to glow. And that's what we then see when we're observing it. And you can see this in the picture here. We've got this sort of circular, almost shell of material of these different colors, depending on what the material is and how it's ionized. And then in the center, we'll have this white dwarf. So that's the planetary nebula. And it was seen to be a completely different type of object to nebulae and galaxies and such like, both with the advent of better telescopes, so you could make out more of the detail, but also with spectroscopy. Because if you do a spectral analysis of a planetary nebula, it looks very different to a galaxy. In a galaxy, you'll get a continuum with lots of absorption lines. Whereas if you look at the spectrum of a planetary nebula, you will see very prominent emission lines. Most notably, you get an emission line at 500.7 nanometers. And when people were first seeing this in these stellar spectra, or these spectra of planetary nebulae, this was something new. People didn't really know what was causing this emission line. It didn't match up with any of the known emission lines. And that's not an unusual situation. I mean, that's how helium was discovered when people did a spectral analysis of the sun and they saw lines associated with helium, but they didn't know about helium at the time. So they investigated elements on Earth and then found, oh yeah, this matches up. This must be helium that's in the sun. So it happened before. But when people started looking around, well, what could this be, doing experiments on Earth to try and create this emission line? Well, this was proving elusive. So it was, well, is this a new element? Is it something, that hasn't been discovered at all that we need to add to the periodic table? Well, it turns out no. It's a familiar element in unusual conditions. So if you've got oxygen, and we're talking about here twice ionized oxygen, so O2 plus, and you have O2 plus at very low density, the sort of low densities that you're going to get in a planetary nebula. Because here we're talking about hundreds or a few thousand particles per centimeter cubed. This is very low density. It might be normal for a nebula, including star formation regions as well as planetary nebulae, but compared to the sort of densities that we can produce on Earth, even with a vacuum pump, this is lower density, much lower density than that. So these are the sort of conditions that we're not creating on Earth. If you get twice ionized oxygen at that sort of density, then you can get what are called forbidden lines. So these forbidden lines are when you're not getting the sort of energy level transitions that you would expect. There are fewer collisions going on. You don't get the same sort of de-excitation due to collisions between these different ions. And you can get some lines, such as this oxygen line at 500.7 nanometers, which then become really dominant in the emission of these planetary nebulae. So this would be an O3 line. Remember, we spoke about these before. So this is referring to the ionization state. So O1 is neutral oxygen, O2 is once ionized. In this case, we've got twice ionized. So this is an O3, an oxygen 3 emission line. And when people are observing planetary nebulae, if you try and look at the Ring Nebula, with the one in the picture here, even through a backyard telescope, you might be able to see it, but it won't look that great. If you put on an oxygen 3 filter on your eyepiece, and they're not that expensive, you could probably pick up one secondhand for about 30 quid, something like that, maybe less, and you put that on the eyepiece, then all of a sudden the detail in the planetary nebulae will come out much stronger. It will have much more contrast. You'll be able to see the shell around the central star in much more detail, because so much of the light which is being emitted is at this particular wavelength. So that's all that the O3 filter is doing. It's saying, right, well, let's let through light of that particular wavelength. So we're just zooming in, we're focusing in. Zooming is the wrong word because we're not increasing the magnification, but we're concentrating on the light that's coming from the planetary nebula and cutting out everything else. So yeah, that's something that then put people on the path to identifying that this was a particular type of object, because there aren't loads of them around, although this is the endpoint for most main sequence stars. So there's a lot of stars that are going to end up ending their lives in a planetary nebula phase. They don't last for all that long. The white dwarf isn't fusing any elements anymore. It's cooling down. It's very hot, but it's cooling down. And eventually it won't be hot enough to ionize the gas anymore that's around it. And the planetary nebula will just become invisible. It won't be glowing anymore. So these things last, a few thousand years, tens of thousand years, and then they just disappear, and the white dwarf just dies. So there's a lot of them around, in at least at different points in time. I think there's been a few thousand have been identified currently in the Milky Way, but that's out of 200, 300 billion stars. So, and there's 2,000, 3,000 of them around, because they're short-lived. They keep getting replaced, but they're short-lived. And that makes it quite hard to tell how far away they are as well, because there aren't that many of them to be able to compare. There's variations in what you see in the spectra of planetary nebulae. So by the time you've classified them in different ways, there aren't that many to really get a good handle on how far away they are. So yeah, distance determination is not that easy. So let's run through a few more. Let's show a few pictures of the famous ones then. This is, which one? This is Dumbbell Nebula. Yeah, so distinctive shape. Again, you have to use your imagination a little bit on these, but you've got, broader. You can see it's got a shape that's looking a bit like this. So it gives that dumbbell impression because it is brighter in some areas than others. You've still got an overall sort of spherical shape, which is what you'd expect in a planetary nebula. But yeah, it's a bit more, it's got the brightness not as evenly distributed. So yeah, this is a Dumbbell Nebula, that's M27. So that's another popular bright planetary nebula. There is Helix Nebula. So we got the Helix, which is another one which is, yeah, it's popular, it's quite bright. Again, lovely range of colours. You can see they've all got a similar sort of look. That looks a bit like the Ring Nebula, but a bit less ring-like. And the last one then I'll show is, this one became famous. This is the Eskimo Nebula. And that's because it looks a bit like a face with a big furry sort of hood going around it. Maybe not when it's zoomed in with quite this amount of detail, but if it's a little bit fuzzier, it does look like a face in a furry parka hood. So Eskimo Nebula. This was a particularly famous picture that got released in the late 90s. Hubble did this is probably the actual Hubble picture. So this was just after Hubble had been repaired, had that problem with the mirror, and it got repaired during the mid to late 90s. And then it was producing all these amazing pictures, and this picture of the Eskimo Nebula was certainly one of them. The detail in this is just nuts. So you've got all of these different levels then of the actual shell of the planetary nebula, this big circular bit on the outside, all of this detail then around the central star here, the white dwarf in the middle. So you'd never see anything like that through a standard amateur's telescope. But there you go. I mean, that's the sort of detail that Hubble was pulling out in these observations of planetary nebulae. So yeah, they're really nice objects to look at. It's difficult if you're an amateur astronomer, particularly if you're in an urban location. You're not going to pull out any detail, anything like this. You will be able to see the Ring Nebula and quite clearly make out the ring if you've got an O3 filter. But again, you won't be seeing those sort of colours. It might be one of those ones where you're having to use a little bit of averted vision, just looking slightly off to the side just to try and pick out a bit more of the detail. I mean, you will be able to see that it's a planetary nebula, but yeah, not much more than that. Okay, it's great if you can go to a darker site in order to look at it, but we don't always have that luxury. So there you go, another deep sky object, which just looks great in the astronomy magazines.